So in this um, recorded lecture, I'll briefly break down the assumptions. So these assumptions are very important Hmm. for the objective point of view because we are going to have 40 MCQs in the exam paper, and um, you can expect like 5 to 10 MCQs on these assumptions. So, but before diving into those assumptions, I'll quickly break down the idea of the accuracy and the precision. Accuracy is about how close you are to the actual value. Like if you predicted something, you predicted you're trying to predict the salary, and the salary was 100 rupees, for example, and you predicted as a 99, 98, 97, 101. Like you can of course overestimate. So these are predicted values. And these predicted values are very close to the actual value. And here you are accurate, right? You're very close to the actual value. But the precision is a different concept, and precision, you can be wrong. Like your estimate can be wrong, but you can still be precise. Because if you're predicting 125, or maybe you're predicting 75, you are not accurate here. But in the first iteration, if you predicted 75, in the second iteration you predicted 74, in the third iteration you predicted 76, in the fourth iteration you predicted 72. So here in this case you are precise, because although you're hitting the wrong number, the wrong target, but you're consistent with hitting that same spot, right? So precision comes from the consistency part. Like simply, if you could just look at the figure number 1 and 3, you are precise here. Although in the third figure, you are not accurate, but you're precise. In contrast, in second and fourth, you are not precise, but you are accurate in the second one, but you are inaccurate in the fourth one, right? But the idea is that you are not precise because your arrows are not consistent. There's a huge difference between each arrow. Like first arrow is at the bottom right, and the next arrow is at the lower left, right? So there's a huge difference between both. So you're not really precise with your targeting the spot, or like the value, whatever it is. So this is the difference between the precision and the accuracy. Now moving forward to the assumptions. So now these are very important assumptions. So whenever you make your regression model, which is written over here in a general format. So so here the idea is that this OLS, ordinary least square, this is a technique. And sir asked about it, like what it is. It's a technique to estimate your coefficients in a way to minimize the squared error, right? So this is what OLS is about. Like this is a technique to estimate your this betas. OLS is a technique to estimate the value of these betas from the data, right? So for example, if I am estimating my salary, and I have the years of experience in X1, the years of education in X2, and so forth. So I'll estimate the value of the beta 1 from the data of the X1, which is years of experience in this example, right? And to estimate the value of the beta 2, I'll consider the data of the years of education, and I'll estimate the value of beta 2 through a system or a method which is known as OLS, ordinary least squares. And the idea is not just to estimate the values of the coefficients, but also in a way to minimize the squared error. right? So I have two goals. I'm not just through OLS, I'm not just estimating the values of the coefficients, but I'm also estimating the values of the coefficients in such a way. I'm estimating the value of the coefficients in such a way to minimize the squared error. So we're not uh, deep diving into the maths, but just like you need to be very clear on this. OLS, the objective of the objectives of the OLS to estimate your coefficient value through the data for each variable and to minimize the squared error, which is this, right? So this is what the OLS is about. But this OLS, when you practically run the OLS, it runs on few assumptions. And the first assumption is that no omitted variables. No, I think most of us are very clear on that because when I told this before as well, like when you're trying to estimate the income of different people, right? Or maybe let's just take our class, the class of FMG and supply chain. We have a different people working in different industries. And if we try to build one single model which applies at everyone, right? We take the salaries of the every person, every student, and we try to come up with a model. And in that model, I'm including the years of experience, the years of education, the city they belong, the company they work in, the metropolitan city, and all other factors. But still, I am going to miss something. Like from my side, I'll try to cover every possible factor, like on which I can collect the data. So one need to make sure that I have all the variables available, the data of all the variables available in hand, which can possibly affect the salary of the students in our class, right? It can be anything. So so we need to make sure that whatever is in our capacity, we need to make sure that the data is collected on those factors and we include those factors into the model, because whatever we are missing in the model, it's going to translate into the error term. And what is the objective? Objective is to minimize the squared error, right? So this is the objective. And to achieve this objective, we need to make sure that we are covering all possible effective factors. Like when we talk about salary, the most effective factors are very obvious: the years of education, the years of experience, the university they attended, and many others. Like you can think of, like it's more of a theoretical work, but this is what the non-omitted variables mean. Because if you omit very obvious variables, so for example, if I do not consider the years of education, so that beta is now missing from your model, right? And that, because that beta is missing from your model, now this the effect of the years of experience is now going to translate into your error term. That is contradictory from your objective of the OLS, which is supposed to minimize the squared error. It's the error and the squared error is the same thing. I'll explain it for later in this video, like why we are squaring the error term. That has nothing to do with right now at least. So, and the second one is the correct functional specification. Model fit the situation at hand. If you could recall, there's one practice that sir made us to do in the class. Um, there was a a quadratic function, and it has a different sort of a data points. The data points were similar to like this, right? And but we were fitting a linear line like this. So sir told us to fit the data, right? And that data was fitted through quadratic equations, right? Quadratic terms. Through the quadratic term. So this is what it means. Look at the pattern of the data, right? And by looking at the pattern of the data, consider, like, do you need some quadratic term? Maybe you need some log term. Like you need to fix the model. If you just remember that example, the quadratic one, so because everyone wrote the equation as well. So in the equation, you were including x squared. So some square of some variable. I don't really recall what exact that variable was, but you had some squared variables in your model. So what you were doing, you were basically adjusting your model according to the situation of the data, right? So this is what the second assumption is about. Make sure the data is presented in the correct format. If it requires a logarithms, do add the logarithms. If it has some exponential effect in it, do add the exponential term. But it's, of course, it's not going to get on that level of complexity. But just for the sake of understanding, this is what we mean by the situation at hand. And then normality. Now this is important again. And assumption says that the error needs to be normally distributed. And I have explained very like in detail about what normal distribution is about. It's going to be centered around some mean. But in this case, the preferable mean is zero. The idea is when you estimate the salary, let's just stick to the example of the salary. And when you try to estimate your salary, the error term is basically your error is your original salary minus your predicted salary. So for example, if my original salary was 100, my Y was 100, and through this model, my predicted value was 90. So 100 minus 90 equals to 10. And for my another colleague, right? For my another colleague, let's take an example of Afaq. Afaq's salary was 110. And through this model predicted the Afaq's salary as 120. So the error here is 110 minus 120 is minus 10. So if I just take these two examples, and if I take the average of both, because mean so if I just take two data points, by the way, two data points are not valid points, because we actually need more data points. And if I just take the average of these error terms, so 10 plus minus 10 upon 2, because the sum in the numerator is going to equals to 0, so my mean is going to be equals to 0. So in this case, the when I plot the error terms, it will be centered around zero mean, right? So my overall model is perfect when my error term is normally distributed. Because if I talk about my model in general, my overall model in general, if the error terms are normally distributed, that means the mean of the error term is centered around zero, right? So maybe it's overestimating for some values, but it underestimating for many values. So when they will add up, it will become equals to zero. And because the sum is equals to zero, in the numerator now you have zero, regardless the number of the values. Like if the sum, how do we calculate the average? The sum of all values, the number of values, right? If my sum of values is zero, regardless of the number of values, and the number of values could be 1,000, I can take the data of 1,000 people, my sum is still going to be equals to zero. So it's a normal distributed, standard normal, and it's centered around zero. So this is really important assumption for my overall model. When my error term is normally distributed, I can say that my model is very good model overall in general. Not for particular case, like for example, in my case, it was underestimating by 10 units. But if I look at the overall picture, it was really nice because the error was zero. The mean error was zero. It was normally distributed. But in some case, it can be centered around 5, 6, 7. The idea is it needs to have normally distributed. So that's the third assumption. And then we have homoskedasticity. Errors have a constant variance. If I explain it through a very basic example, so what it means is um, the variance of I would say given xi should be equals to, yeah. This is how I mathematically would write it. But if we try to break it down, if we try to break it down, homoskedasticity means that if my x is changing, like x can be any number, right? For example, age. If I just take an example of age, if my age is x here, right? If my age was x, my x, and I have five data points. I have age of 5, I have age of 10, age of 20, I have four different data records, and these are the ages of for each record. First was child, again child, a young boy, and middle age. So when I predict my model, when I predict a value by for each age, for age of 5, for age of 10, for age of 20, for age of 30, the error should be constant, and it does not rely on the fact that I'm really switching across the ages. So mean is, so here the fact is, if I'm changing my x value, because x is of course is going to get changed, my age is not going to get constant. My age is 22 years old. My other colleague's age is 45 or 43. If I if I apply my model through my on my age and on my colleague's age, the error should be constant. The error should not fluctuate. The model is supposed to adjust itself, right? So that's what the homoscedasticity means is your variance, the variance of the error. We're talking about the variance of the error, by the way. So when I'm changing the age, because of course, like if you look at this model, if you look at this model, if x1 was my age, and in the first prediction, I was putting x1 equals to 5, and in the second x22 for my age, and for my colleagues' age, it was 43. So my Y is going to be a bit different, right? And of course, our salaries are different. And when I take the difference of for both cases, the error term should be constant, and it should not drastically change, because if it drastically changing, that means it is correlating with the values. This is the condition of this one. This is how mathematically we write the heteroscedasticity, right? This is a violation of OLS. This is homoscedasticity. This is acceptable, the green one, and the yellow one is not acceptable. In the green, what it's saying is, as you change the values of the xi, your error term is not going to change, right? But yellow says if you change the value of your x, the error term is going to get changed, which is violation to the OLS. And I've like break it down through the example of my age and my colleague's age. If my salary was 100, right, and my age is 22, so when I predicted from my model, from this overall model, the prediction was 98, right, and the error is now 8. But when I come here and I try to predict for my colleague whose age is 45 and whose salary is 1,000, right? and the model predicted 992. So the error is still 8. So it has nothing to do with the age number. Although my xi is changing here, my in the first calculation my xi was 22, and in the second iteration my xi was 45, but my error remains 8 in both cases. My salary was 100, my predicted was 98. His salary was 1000 and predicted was 992. So the error in both cases is 8. So it does not depend on the value of xi. So this is homoskedasticity, and this is what we need. I think the spellings goes wrong, but this is what we need in our model. And if this goes violated, then the second situation is heteroscedasticity, which is violation to the OLS. So this is what we means. And then we have no autocorrelation. No autocorrelation when when the errors start correlating with each other, right? My if so you can think of it as if I made a mistake in my first model, right? I keep making the same mistake in my other iterations. So that error is going to translate, right? I'm making the same mistake in every exam paper. So my mistake is consistent. So that's a problem. Like you're literally making a same mistake again and again, and that's a problem with your model because your model is violating one simple fact again and again. In regression models, error is not a bad thing, right? Error is going to be there. You cannot perfectly predict anything, but the nature of the error is concerning. Like we're concerned with the nature of the errors. Errors should be random. Like error is going to be there, but it should be random. It should not be correlating with each other, because if they are correlating, that means you're making the same mistakes over and over again. That's a violation. So this is what the correlation mean. When you autocorrelation mean when the errors start correlating with each other, and they will start correlating with each other when you will be making the same mistakes over and over again. So that's why we need no autocorrelation. And then we have low multicollinearity. It's like literally simple, like X variables are not highly correlated with each other. So basically, like if you are in your regression model, you have maybe, for example, if you have in your model, if you considered your BMI, the body mass index, I assume that it's the ratio of the height and the weight, I guess. I'm not like I think it's height and weight. So BMI is a body mass index. I'm assuming that it's the ratio of the height and weight. I can be wrong here, but just cross check. But it will serve the purpose. So BMI is the ratio of the height and the weight, right? I have included this in my model, but then I am also including height and weight separately. So these are going to be correlated, highly correlated with the BMI. Can be. Like I'm just giving you an example. So these are the cases when the correlation happens. So I have X1 BMI, I have X2 height, and I have X3 weight. So these variables will be highly correlated with each other. And that's a bad thing because you're literally trying to put the similar you're literally feeding the model with the same variables data, which are very correlated with each other, and it's just going to become inefficient model because your R square will keep increasing without any major improvement in your R square, adjusted R square. So that's where the problem comes in. So you need a low multicollinearity. So in years of education and years of experience, you can expect a low collinearity. Although you are like it's very obvious that both factors are very important to determine the salary, but they are also less correlated with each other. And the next is no micro numerosity. Number of observations sufficiently large. That's very obvious. Like you need a like reasonable sample size. right? You cannot, try to see the patterns based on two or three or maybe 10, 15 observations. You need like 30, above 30 or 100, in hundreds and thousands of observations to actually see the patterns. And plausibility is about X variables have a plausible relationship with the dependent variable. Of course, like these, the low multicollinearity, the plausibility, these are like with the these are related with the intuition. I mean, like as a, and that's not really, I think from the project point of view, that's really important for us as a but to have a good understanding of this, because we will be choosing the independent variables and the dependent variables ourselves. So the plausibility, the collinearity, so these are the things that we really need to put them in work while making our while coming up with the idea of our project and executing the project. But from the exams point of view, like it's literally written here in the line. Yeah, so these are about the assumptions, and you just like literally need to understand, like have a solid concept of these assumptions in your mind. Homoskedasticity is it can be a difficult concept, but I think we have done it quite well. Like just remember these green and yellow one, and then the example we did for each case. Like your error should not be correlated with the value of your x. The the age value you're going to put into your model shouldn't be correlated or have anything to do with your error, right? So this is the crux of the homoscedasticity. Let's just quickly look at the graphs. Like if we're talking about the autocorrelation, how does it looks like? Because in objective case, sir can like show us a graph and tell us which one is a violation of the assumption. So when we talk about the autocorrelation, so this is how autocorrelation in error terms looks like. So you see a trend, right? That's a trend. Increase, decrease, increase, decrease. This is also a trend. Zoom in. Okay, I see. So this is also a trend. This is also a trend. This is no autocorrelation. Like literally, this is your line and it's randomly placed. The points are randomly placed. You cannot really see a pattern, right? Here you can see a pattern. Here you doesn't really have any pattern. So it's no autocorrelation. The error terms are not correlating with each other. It's purely random. Now look at this. This is now again heteroscedasticity. Heteroscedasticity means your xi will have an effect on your error term. This is what the heteroscedasticity means. And this is a violation of your assumption, right? So by looking at these graphs, you need to tell like which one is not heteroscedasticity. This is heteroscedasticity. This is again. Now, this is not heteroscedasticity. This is homo. Like there's no pattern. I mean, look at the line. As you moving from the line, it's decreasing and then increasing. There's a trend here. As you moving from the line, as you're moving through from this line, like this means at x went closer to zero, and as you keep increasing the value of x, the error term is decreasing. So that's a violation of homoscedasticity, right? In this example, as you keep increasing the value, right, your error term is going to get increase. So that's a violation of homoskedasticity. And the violation of homoskedasticity is heteroskedasticity. So as you keep increasing the value of x, this is x, the values of xi, as you keep in moving towards the right, your error term is exploding. So this is not a right indication. Similarly, this is not a right indication. This is not a right indication because your error term is correlating with the value of x's, right? The data points. Xi's are the data points. Similarly, this is about the normality. I have already explained the normal distribution in the previous, like how does a normal distribution looks like. I think we don't really need to understand that. It need to be symmetrical bell curve. Oh yeah, so this is regarding your second assumption, which is basically the situation at hand. Like you need to look at your data points and to fit that way. So again, if you recall the example that we did in the class, we have this type of data, and then we end up fitting a line which looks like this, which was looking like this, right? So that's just the way how we look at the data points and try to adjust according to the data point. So it's a violation. Like here we have sort of a quadratic. Here we have a linear or positive linear, right? This is correct. This is not correct. The red line here is not correct. The black line is trying to adjust thing. So black line is correct, but the red line was a violation. Like you cannot really fit the red line here. You can fit the red line here, but you cannot really here because you can see a pattern or a downward trend, a quadratic again, or maybe exponential. So yeah, so this is about the trends and everything. And this was about the assumptions.